Welcome back. Lesson 18 Binomial Coefficients and Pascal's Triangle. Introduction. Recall the number of R combinations from a set of n elements is often denoted by parenthesis n, choose R. This number is called a binomial coefficient because these numbers occur as coefficients in the expansion of powers of the binomial expressions such as a plus b quantity power n. A binomial expression is simply the sum of two terms such as x plus y. Here is an important theorem, the binomial expansion. Let x and y be variables and let n be a non-negative integer. Then x plus y quantity power n is equal summation j equals 0 to n choose j x to the power n minus j y to the power j, which is actually equal n choose 0 x to the power n plus n choose 1 x to the power n minus 1 y plus so on. Basically, if you notice, I want to achieve degree n using x and y. So either I have no y or 1 y or 2 y's or n minus 1 y's or all of y's. That's what is happening. So choosing 0 from n, choosing 1 from n, those many x to the power n or x to the power n minus 1 y will happen. And that's how you get this expansion. What is x plus y power 5 equal? Well, all we need to do is use this formula. What is x plus y power 5? By the binomial expansion formula, it is x to the power 5 plus phi choose 1 x to the power 4y plus phi choose 2 x to the power 3y squared plus phi choose 3 x to the power 2y cubed plus phi choose 4 x to the power 1 y to the power 4 plus y to the power 5. So notice how you start with a degree of 5 for x and systematically reduce while increasing the degree of y until you get y to the power 5. So 5 choose 1 represents y to the first power. 5 choose 2 represents y to the second power, and so on. Well, the rest is just formula. 5 choose 1 is 5. 5 choose 2 is 10. 5 choose 3 is also 10. 5 choose 4 is 5. And 5 choose 5 is 1. What is the coefficient? That's the next question. What is the coefficient of x to the power 12, y to the power 11 in the expansion of 3x minus 2y, the whole power 23? Well, I want whole power 23. All right. So x to the power 12 and y to the power 11. So together that's 23. How do I get y to the power 11? Well, the second term has to be taken power 11. That is, I am looking at choosing 11 from 23. Don't forget y comes with its own negative 2. X comes with its own 3. So when y has power 11 and x has power 12, 3 gets power 12 and negative 2 gets power 12, power 11. So 23 choose 11 is, by the way, same as 23 choose 12 because 11 plus 12 is 23. Okay, so that's why you can write 12 here or 11 here. They are both okay. 23 choose 12 is same as 23 choose 11 because 12 plus 11 is 23. So anyhow, odd power of a negative number, the negative comes out. This is the coefficient of x to the power 12, y to the power 11. Corollary. Let n be a non-negative integer. Then summation k going from 0 to n choose k is 2 to the power n. Let's prove this. This is straightforward. Corollary means that which follows. That which follows your theorem. So in this theorem, suppose I take x equals 1 y equals 1. Then I get 1 plus 1, that is 2 to the power n. That gets me the right hand side. That's all. 1 plus 1 is 2 to the power n. 1 plus 1 power n is 2 to the power n. Moreover, this expression now becomes k going from 0 to n choose k, see j is k, x is 1, 1 to the power n minus k, y is also 1, 1 to the power k. All of that is actually 2 to the power n because this is equal to this in turn is equal to this. 1 power anything is 1, so it doesn't contribute anything. So all I'm left with, summation k going from 0 to n choose k is 2 to the power n. Next corollary. Let n be a positive integer, then summation k going from 0 to n negative 1 power k n choose k is 0. Well, how do I get negative 1? If I copy this, instead of plus, I need minus. 1 minus 1 power n. Well, 1 minus 1 is 0, so it's 0 power n. 0 power n is nothing but 0, and that's where you get the 0 from. On the other hand, using binomial coefficient, binomial expansion, what do I have? Summation k going from 0 to n choose k, x power n minus k, and y is a negative 1 power k. 1 to any power is 1, there's nothing to do, but negative 1 to the power k stays, n choose k, all of that is 0, which is what we wanted to prove. Next, look at this. Let n be a positive integer, then n choose 0 plus n choose 2 plus n choose 4 all the way until n choose is equal n choose 1 plus n choose 3 plus n choose 5, so on. Notice all of these are even numbers you're choosing, and here are odd numbers you're choosing. Well, this corollary follows from here, the corollary we just proved. Okay, how so? Well, expand this corollary too. When you expand it, when k is 0, I get positive. So n choose 0, k is 0. When k is 1, I get negative n choose 1. When k is 2, that becomes positive, n choose 2. When k is 3, I get negative, and so on. So I alternate between positive, negative, positive, negative. So notice what is positive. Whenever k is even, I have positives, you see, and all the odds are negative, and all of that is equal to 0. So take the negatives, move it to the other side. So all the odds are here, all the evens are here, and that's what this corollary says. Next, theorem. Let n be a non-negative integer, then summation k goes from 1 to n, 2 to the power k, n choose k is 3 to the power n. Something is off here. This is obtained from here, 1 plus 2 to the power n. That is, k goes from 0 to n choose k. So all I have used is the binomial expansion, x1, y2. When you do this, you get k going from 0 to n choose k, 2 to the power k. So it should be 0 to n. All right. Lastly, Pascal's triangle. This is a beautiful result. Pascal's identity and triangle. Okay. Let n and k be positive integers with n greater equals k. Then n plus 1 choose k is n choose k minus 1 plus n choose k. This is a very important identity, but it's easy to understand if you think what n plus 1 choose k represents. It represents the number of k element subsets of a set S with n plus 1 elements. So suppose you have a set S with n plus 1 elements. You want to collect k element subsets. how many such subsets can you collect? That's what this binomial, that's what this combination represents. This is, after all, a combination. You are choosing k element subsets from a set consisting of n plus 1 elements. Okay. Now fix an element. Now n plus 1, so it's at least 1. Fix some fixed element in S, let's call it x. Now a subset of S could contain x or may not contain x. So take a k element subset. It may or may not contain x. So what if it does not contain x? Well, if it does not contain x, then I'm choosing k elements from n elements because that x is the n plus first element. So n choose k represents k element subsets from a set containing n elements. So that x is somewhere away. Okay. Now you throw in the, so either you have the x or you don't have the x. Now if your k element subset has x in it, then the remaining elements are k minus 1. So you are choosing k minus 1 remaining elements from the remaining n elements of S. And that's what this number represents. So I hope this is clear. Let's do a small drawing. You could have, so here is your set S. Which has n plus 1 elements. Of those, this one is x. The rest is n plus 1 elements. The rest is n. This is n, this is x. So n elements and one more, n plus 1. So your subset, k subset, could all sit here, or it could take that one element and the rest sit here. So these are k, all of the k are here, or k minus 1 are here, and 1 is that x. That's what this is. K minus 1 subset from a set of n elements, that's this count, and k element subset from the set containing n elements. So together you get all the possible k element subsets of the entirety of S. Okay. This Pascal's identity is very important. Notice n plus 1 choose k is n choose k minus 1 plus n choose k. So this is Pascal's identity. Place 0, 0 here. 0 choose 0, that's 1. 1 choose 0 and 1 choose 1, that's here. 2 choose 0, 2 choose 1, 2 choose 2. What does that mean? Here are k's, here are n. So as I go down, n increases and k increases left to right. Our result here says n plus 1 choose k is equal to n choose k minus 1 plus n choose k. In other words, anybody here, this is n plus 1. That's n, that's n. So n plus 1 choose k is same as n choose k minus 1 plus n choose k. So this number is equal to this plus this. That's how you build your Pascal's triangle. 0 choose 0 is 1. Write 1, 1 here. Look, each row, this 3 is obtained by adding these two. This 3 is obtained by adding these two. Continue. 4 is obtained by adding these two numbers. 6 is obtained by. So you get what is called Pascal's triangle. Okay. So this completes lesson 18. We will meet in the next video with lesson 19. Until then, bye.